So think of it like baking a cake. When you bake a cake, you have the temperature, you watch the cake. Imagine a cake has a lot of layers. Well, if the oven's too hot, some layers are going to burn and the inside's not going to get cooked because you don't get good conduction through the heat. So what you want, even when you bake a cake, you still have to be careful to adjust the temperature right to make sure that the layers all cook it the same way. And it's the same idea in a model.
All right, everyone, welcome to another episode of the TWIML AI podcast. I am your host, Sam Charrington. Today, I'm joined by Charles Martin. Charles is the founder of Calculation Consulting. Before we get going, be sure to take a moment to hit that subscribe button wherever you're listening to today's show. Charles, I am super excited to have you on the podcast. We've been working on this one for quite a while now.
Great. Thanks a lot, Sam. I'm really happy to be here. This is a great show.
Appreciate it. To get things started, I'd love to have you share a little bit about your background and what you've been up to recently with our audience.
Sure thing. So, I'm an AI researcher. I did my PhD at the University of Chicago. You may know my more famous classmate, John Jumper, who just won the Nobel Prize for AlphaFold. I then was an NSF postdoc. You may know another classmate of mine, Jürgen Schmidhuber, who basically claims to have invented everything else. So I did my. So I've been doing this for a very long time. I've been working in the industry. I left grad school and postdoc, went into industry. I've been doing consulting work, building AI and machine learning solutions for companies forever. I did Aardvark, was acquired by Google. I did eHal, first $1 billion IPO since Google and probably the biggest crash. I was a quant on Wall Street. I was also been scientific advisor to Larry Page's family. So, and during the course of that, about 10 years ago, I decided to get back into AI research, working with my friend Michael Mahoney at UC Berkeley, very informally. And we've been working on this project called what I call the WeightWatcher project, which is an open source tool. We have almost 200,000 downloads, which is designed to help people who are monitoring, training, and fine tuning their own AI models. And all of this has been just really a passion project to get back into research using techniques from theoretical physics and chemistry to understand how these models work and how to help my clients.
And you've been at this for a while. I think we first got to know one another in the deep learning era. Now we're all talking about these large language models. How does this stuff apply to LLMs?
Well, it actually works really well. I did theory, but as a theorist, I work with engineers, so I know that theory, they say, in theory, practice and theory are the same, and in practice, they're different, right? So I actually got into this. I had a client in all places of Slovenia, and they were making like fake text for things like weight loss articles, Amazon reviews, things like that. So this is before even like OpenAI stuff came out. And we're generating this text. I realized I'm generating like 50,000 pieces of text a day. I have no way to know if what I'm generating is any good or not. And I can't hire 500 people to evaluate it, so it would blow my costs. I've got to get a theory. I've got to invent some kind of theory that would let me know whether these AI models are working correctly or not. And I started working on my spare time and working on, kind of cracking the books and, acting like a scientist again. And that's where it's come up. So it turns out it applies really well to LLMs because they're really big and they have lots and lots of layers. And this is basically theory which analyzes the weights in the layers. It's WeightWatcher. So it looks at the layer weight matrices. And so the more layers you have, the bigger the model, the better the theory works.
It's kind of interesting to me that even in that, practical context, so working with a client that has a job to be done as opposed to in academia, the approach you took was a theoretical approach as opposed to a more, let's call it a statistical approach, like the application of evals as a practice as opposed to the theoretical take on it.
I did all this stuff in the 90s, and I have this background in theoretical physics and chemistry. So, and of course, I was a quant on Wall Street. So some of the techniques I'm using actually are quant techniques that we used on Wall Street to predict the markets. So I knew how to apply these techniques to real systems because that's what we do. We do portfolio theory.
What's an example of a technique and how is it used on Wall Street and how are you using it in your project?
So in portfolio, when you're like at a big place, I was at BlackRock. That's the 800-pound gorilla on Wall Street, and we have the group I was in. You couldn't even trade in the group unless you had $200 million, right? That was the scale. So it was a big portfolio, and you have these big portfolios, and you have to figure out signal versus noise. Where's the signal in the portfolio versus noise? You're trying to reallocate how much Google, how much Apple, how much GM, how much that kind of stuff in the portfolio. And so you have to decide signal versus noise. And so you use something called random matrix theory to do that. And you can detect the signal and the noise. And it's important that you not peak at the stock market data. You not peak at things because you'll overfit yourself to the history. So there's two things going on. I'm using random matrix theory, is what we do. And I'm making sure not to look at the data. Because if you look at the data, you'll fool yourself, right? You'll think, So that idea is actually essentially, you can think of WeightWatcher as and trying to find the signal from noise in a model by looking at the individual weight matrices, which are like little portfolios. They're like the portfolios you would form when you're doing portfolio theory. And I knew about some of the theory because we do theory when you're a quant. And so it turned out there were some very interesting and they're interesting scientific properties. As a scientist, I started studying this stuff, and I go, what I did was I just took the models that people had trained. They did these open source models. Right? Today we have Hugging Face. There are 1 million models on Hugging Face. When I started, there were less than 100 open source models. I started looking at them, right? What do they look like? What do the good ones look like versus the bad ones? Just like when you're a quant, what do good companies look like versus bad companies? And you analyze their properties. And it turned out there was some interesting science behind this. And one of the guys I worked with, the guy who's the head of futures and equities at BlackRock, was a theoretical physicist. And, he showed me some of the stuff they were doing. We can apply this to AI. And it just turned out to work, and I just kept digging and digging and digging. It just worked better and better and better. And then I discovered there's some deep science in this. So that's where we ended up.
And so traditionally in the ML AI world, the way to overcome that, overfitting on the past data is to split it into test and train and to only look at part of it. Are you, uh, you're not looking at any of it?
No, no. In fact, you don't do that in physics. Yeah. Like when you do analysis, I have like 100, I have this 120 long, 20-page paper, theoretical physics explains how we do things, but it's actually different, right? What you're doing is you're looking at, it turns out the weight matrices, when you train a model really, really well, the weight matrices have these universal properties. I call them signatures of emergence. And they actually, this idea actually comes from because I did AI in the 90s, I know something about neuroscience. It turns out these signatures are very similar to the signatures you see when studying spiking neurons. And it turns out spiking neurons exhibit something called parallel structure, and they have these sort of universal properties, and we knew about them. And sort of the original tools, I took these tools from computational neuroscience, and I just applied them to the layers of weight matrix. And it turns out they have the same signals. So it turns out that the spatial temporal correlations in the weight matrices, in the layers, in the neurons, are very similar to what you see in actual neurons. Like that you would culture, you take a lab, you culture them, you grow them in the lab, and you look in there. It's the same thing. And this work was pioneered actually by some physicists in the 90s, in particular, a friend of, some guys, a guy named Jack Cowan at the University of Chicago has done a lot of work on this. He's sort of invented a lot of this stuff. So it turns out this stuff works. And it's actually very simple. If you train a model, you're training a layer, right? But most people think of training the model as I minimize the training accuracy. But you
Well,
have
you
to think,
minimize the error, right?
or you minimize the error, right? Accuracy of the error. Right. Excuse me. You minimize the error, not the accuracy, right? Maximize the accuracy, right. So think of it like baking a cake. When you bake a cake, you have the temperature, you watch the cake. Imagine a cake has a lot of layers. Well, if the oven's too hot, some layers are going to burn and the inside's not going to get cooked because you don't get good conduction through the heat. So what you want, even when you bake a cake, you still have to be careful to adjust the temperature right to make sure that the layers all cook it the same way. And it's the same idea in a model, is that if you're training, like for example, if you turn the learning rate up too high, it turns out some of the layers overfit. So they become there's too much information in them, and they just overfit, and all of a sudden they stop generalizing. And we have a very interesting paper that I've done with a fellow who came out of just getting his master's degree now, super smart guy. And he was looking at this and he said, well, why don't I take this old Grokking problem? And it turns out if you take a simple model and you train it for a very, very long period of time, even if you don't turn the learning rate crazy up high, you'll see that it starts to overfit, and we can detect this. And this signature of overfitting, really the reason I started thinking was because, if I were trading in the stock market and I were making an AI model, what's the one thing you don't want to do? You don't want to overfit to the history.
Overfit on a history, yeah.
Because, and I believe it or not, when I was at BlackRock, we saw guys doing this. I'm like, "What are you doing?" Like, "Why you can't even do this stuff and it
Well,
didn't
that's the
work." I'm like, "Of
classic
course."
thing. You learn a little bit of machine learning. You say, let me download all of the historical data and train a model on it.
Yeah, you go like, "Here's a guy, PhD from electrical engineering from Stanford." I'm like, "What are you guys doing?" But this is a classic thing, and so it's very critical to understand when the overfitting occurs. And so that, having been a quant on Wall Street, really, really sensitive to this kind of stuff. And it turns out there's some ideas from physics that are like phase transitions, and where in the stuff we knew this stuff happened in the 90s. Like, we understood the theory. The thing is, we're physicists. The physicists and the computer scientists didn't really talk that much. So, so we have these theories from physics that we know we can detect this stuff, but how do you apply it? And that's what we try to figure out how to do. And it turns out that, yeah, you can detect when the model overfits and when it's underfit. And you can see it in the layers. It's just like you could see this layer is burnt. It absorbed too much information and absorbed so much information from the training data. It got stuck and it doesn't learn anything. It's overfit, right? And then there are cases where the layers are underfit. Like, the bottle's too big or something's going on. The layers just didn't really learn anything. So we can detect that very easily.
So we'll dig into this paper. Before we do that, a context setting question and then a possible rabbit hole. So the context setting question is one application of all this is fine tuning models. And when we were chatting before, you were talking about how fine tuning is really difficult and a lot of folks get it wrong and find it really frustrating. Other folks I hear from say, oh, fine tuning's so easy right now compared to, a few years ago. Kind of square that circle for me and talk a little bit about your specific experience with regards to fine tuning.
So if you look at what people are doing, there's a report by McKinsey that said maybe 9% of companies doing AI are fine tuning. So the rest are probably doing prompt engineering. And the question becomes, look, most people do. I'd say out of those, probably of those, only 9% are really doing full fine tuning on very large data sets. Yeah, you could do something like LoRa, which is called low rank adaptation. And you can kind of tweak the model to, if you want to get a JSON output or you're trying to get markdown output, you can just tweak the model a little bit to change its outputs. You can kind of steer it a little bit, right? But if you want to add a huge amount of data to your model and you want the model to learn from that data while still, keeping its own knowledge, it turns out that it's actually quite hard. It's hard for a number of reasons. One, because I've worked in enterprises, it's hard to get good data in the enterprise. And that's part of it. It's just I just talked to a client a couple weeks ago. He said, "Yeah, we had our model running for a year in production. We had to dump it and start over because we didn't realize it was broken because something happened in the data pipeline. The data pipeline stopped. Somebody changed a column table or they changed something and it screwed up the model." And I've worked with projects like worked with GoDaddy and eBay and Walmart, and these things happen all the time. You're in a production environment, the data changes, you don't know it changed.
Where'd that
Nobody
feature
told you,
go?
you know? 3 months later, the model's not working. What happened? So, this is the problem with fine tuning or even, because, you're or even training your own model from scratch, that the data goes crazy and you don't know it. And that's probably, and then the thing is, how do you prepare good data sets? Data sets they're duplicates and there's noise and there's problems. And so in a real environment, a production environment, in a legacy company, this is very hard. So yeah, if you're just training on a very small data set and you can look at the data yourself and curate it, you could probably get the data right. But when you're in a production environment I've worked like Walmart, millions of examples on the clickstream, from the search engine, you can't curate it yourself. You need tools which let you look at the model and say, did something go wrong? It's very hard because you just don't know. You don't have visibility. The other thing that makes fine tuning hard is just that You never really know is whether you're evaluating the model correctly. There are 100 different evals. And, there's all this controversy, and I remember Llama 4, oh, they put Llama 4
Cook the
out,
books.
they cooked the books, right, they snuck it in, it turned out now and then it turns out that the
Ellen
LM
Marina.
guys,
Yeah,
Marina, they've been secretly handing over the answers, like 25% of the answers to Google and
that's the
and
Cohere
and
paper that
Facebook.
came out a couple weeks ago.
Yes, yeah, the Cohere, I gave a talk at Cohere for AI a few weeks ago. Yeah, so they've been cooking the books, you don't really know what the model can do, right? So
Don't say that though, because they just raised a ton of money in there.
Uh, you know, uh, it's they're trying to figure out, right? They're trying to figure out what's going on. So look, I work with real clients, and my clients, when my models don't work, they don't pay me. Like, so it reminds me of the difference. You ever see the old movie Ghostbusters?
Uh-huh. Of
I remember
course.
they're getting ready to leave the university, and I think it was I can't remember which one of them said. He goes, "Look, man, you've spent your whole life in academics. You've never been in the real world. They expect results." So I'm coming from that perspective. Like, so, it's yes, of course, the problem that's happened is that in the industry is that the tooling has gotten easier. And with the tooling getting easier, there's a lower bar to entry. Everybody's trying to do things. And so there's a much wider variance in what's going on. And so we see that I don't see a lot of people, if they are fine tuning, there's a lot of problems, things break. And the goal of this product was to figure out how to make fine tuning work really well and to detect problems in production. So if you're retraining a model every day, I worked in search engine retrain every hour, but you might retrain your model once a month, maybe once a week, once a month. You want to make sure things didn't drift and go crazy. And this technology is designed to help you find those kinds of problems to find problems you can't find using any other technique.
But one of the things you said that was pretty interesting was uh, kind of the suggestion that there are different types or degrees of fine tuning. Like there's a, surface level fine tuning and a deeper fine tuning. I'm going to force fit your cake analogy. Like you've got a vanilla cake. Do you want just like chocolate icing or do you want chocolate at the bottom layer?
Or you want to stick a layer in between. That's exactly right.
Yeah.
Yeah, if you're just
Yeah.
putting sprinkles on the cake, it's not a big deal.
Yeah.
Okay. But if you're trying to, stick something in the middle, you
And
want
I've
something to
not
jump.
really seen like any like concrete, taxonomy or elucidation of like degrees of fine tuning and or what characterizes an easy fine tune, what characterizes a
Well,
hard fine
you
tune.
have models that are instruction fine tuned. Okay. So instruction fine tuning for us, our technology is really, you're doing instruction fine tuning on 100,000 examples or a million examples. We were working, for example, with a group in Poland, and they're trying to do instruction fine tuning on a model to try to adapt it to the Polish language. And we found there were some funny things going on, like they're trying to do there's a model called Solar, which is quite good, and they were trying to adapt the Solar technology to their model called Biloc, and the model's not bad, right? But something happened inside the fine-tuning and the model training that somehow whatever they did, the weights and the weight matrices and the layer doesn't, and by the way, this is all published in the City Publication, it doesn't look like Solar. Like something went wrong, and we couldn't figure out what it was. Like, what did you guys do? Because you're trying to replicate
It's like
the
you want to
process.
keep what you like about the base model, but add some behavior or add some knowledge or add something at the same time. And it sounds like they broke something
They
fundamental in the
broke
base
something, and the
model.
thing is, you're trying to follow an instruction that somebody else has given you, but you don't really know what's like, you're trying to do something a little different, and it's difficult to make the recipe exact, right? You change something a little bit, and now, you used a different kind of flour, a different kind of oil, a different kind of butter, something went wrong, and you don't know why. And this stuff is so ephemeral, it's so opaque. Whatever you do on one data set might not work on another data set for whatever reason. We don't know why. And that's what we see happening is that they tried to replicate the training process exactly. But when you look at the models, well, they're quite different. What happened?
And
So we're
they're
trying to
quite different in terms
the
of
the WeightWatcher spec,
behavior and performance or some
the
from the
internal
perspective
structure.
of your yeah, yeah,
Yes.
yeah. So one thing that this tool does is it makes clear some set of differences between these two, what they started with and what they ended up with
And the
that
problem is that you don't know what the problems are gonna be until you go into production and people start doing things. There are a million things you could do. You're trying to like I said, you're generating fake text, you're answering questions, you're doing things. You don't
So
know how it's
did
gonna respond.
they were
So we're still
they
it's a research
already a
project.
client of yours and, like, it was natural to use WeightWatcher? Like, were they using WeightWatchers from the beginning, and so it was clear what was
No, no, they
happening?
came in later. What happens is they're doing it, they train the
What did they
model.
see then? Yeah, what did they see
Well,
that
what we
said, "We
see
need
is
help with
look,
this"?
the layer Weight Watcher gives you a layer quality metric. So if I have a model with 1,000 layers, and you have some of these models now have 1,000 layers, right? But you have 1,000 layers, maybe 100 layers in your model. Every layer gets a quality metric. What's the score on the layer? And that score should be somewhere between 2 and 4, 2 and 6. And so in that range, 2, yeah, say 2 to 5. Now what you find when you fine tune is you can look at the fine tuning update. So I train the model. Here's the update. I want to look at the update. If the update should show good quality scores between 2 and 4, 2 and 5. If you look at the instruction fine tuning updates of Llama, Quinn, Falcon, Mistral, they all show reasonably good layer qualities. You look at these, even Solar, their instruction fine tuning for some reason had a large number of layers that seemed to be underfit. The layer quality was too high. I should say quality. The quality was low in the sense that the metric was above 6, maybe 9, maybe 10, maybe 15, way too high, which indicates the layer is almost random. So what happened? That those layers for some reason did not learn any information. Or if they learned it, they learned it very weakly. There's only a very small amount of information those layers learned. And that's, you're wasting a lot of compute. You're spending all that. I mean, they're running on a supercomputer in Poland. So, they're spending all this compute, time, energy to figure out what's going on. And that's what the tool is telling you.
But
There's
a
a
step before that, what was the thing that they were observing in the training process that that caused them to call you? Was it just
well,
poor
I think
performance or
yeah, they're just trying to get the performance up. They're trying different things. And again, they don't really know what to do. You read a paper, there's instructions, there's code, but when you run on your data set, it does something different.
so we read this paper. Based on everything we read, we should be able to take our data, apply, a fine tuning approach to it, and see performance like this. But we're seeing performance down here. Can you help us figure out what's
Right.
going
And
on?
so one of the things one of the things people do now is on these big models, they're doing all sorts of, it used to be you take a model, you train it, right? Now people are trying to they tried to replicate part of the model. Here's part of the model, and we're going to take these layers and replicate them and stick them up here, right? And then we're going to take two models, we're going to merge them together, right? So they do all these funny things, right? And then people say, oh, you can replicate layers, you can merge models together. And it's kind of like, that's a little strange, And it turns out it gives goofy results. And that's the problem, right? And you don't know, did you do it correctly or not? They just don't know. You just don't know because you don't really know. Like the recipe doesn't have enough detail and it depends on the ingredients, which are, which change. They're not stable. So that's what makes this stuff so hard. And similar to fine tuning, like if you don't have the exact data and maybe the hyperparameters were wrong, like maybe the hyperparameters for this data set are different from the hyperparameters for our data set. How do we select the hyperparameters? How do we select the learning rates for each layer? Should we have dropout? Should we not have dropout? Should we have weight decay? Should we not have weight decay? These are the open questions, and it changes from data set to data set. How would you know? And this is the kind of thing that we found that it was very difficult to try to, and especially because you're running on a supercomputer, you could run it once, right? On the computer, it runs for a few weeks. You come back, oh, you're not Google. You can't run it 100 times on their million node cluster.
I mentioned that I had a possible digression rabbit hole, and that is when you were describing the spiking nature of the neural networks. It made me think of like Numenta, the Jeff Hawkins stuff. Like, have you come across that? Like, are
I've met them at
there
conferences. I like what they're doing. It's look the idea of modeling spiking neurons was developed by a guy named Jack. There were sort of two or three people at the time in the late 1960s. And one of them is Jack Cowan. If you follow Schmidhuber on Twitter, he was complaining that Hopfield got the Nobel Prize and he deserve the Nobel Prize. These guys, What are you going on Twitter? He's also, what are you going on Twitter saying stuff like this? I mean, come on, man. I mean, that's something you say for a bar when you're drunk, not when you're on Twitter. Um, but during the late 60s, people started modeling neurons. You'd go in the lab and you would model the spike electrical activity and try to come up with models for the electrical response or neurochemical response of a neuron. I was a theoretical chemist. That's what we do. Is what theoretical chemistry does. So it turns out that people have like models of spiking neurons, and there are people. I mean, but I mean actual neurons, like in a lab. You would take the neurons, you grow them in a lab, and you put electrodes in, you watch how they spike, right? Some Elon Musk kind of thing. He's going to try to, how they know how to,
Neuralink, yeah.
yeah, how it works. That started by growing neurons in a lab, right? That's where it comes from. That was like the early work on this. So, there actually is a deep connection between that stuff and AI. People, yeah, and the models we have today were developed to try to explain these spiking neurons, and they eventually became sort of computer sciencey models, and we run them on, GPUs. But there's a lot of theory behind that, and there's a lot of experimental observations, and you can observe what I call signatures of emergence. These signatures, there's a book by a guy named a late physicist Purbach, and he invented a theory called self-organized criticality. And it's this idea that systems self-organize to a critical point between order and chaos. And you can see the signature of this critical point between order and chaos inside many physical systems, in particular things like avalanches. The snow is falling on the mountain, all of a sudden it collapses. And there's this point right before there's this point right before the critical point when it collapses, where it's in this sort of semi-stable state of self-organized criticality. That's what's going on inside the brain. That's a theory. It's called the critical brain hypothesis. And so we can see these signatures of criticality. I call them signatures of emergence of AI inside actual neurons. And it turns out our experimental work shows that the closer the quality, I have this layer quality metric. There's a sweet spot at 2. There's a value of 2. And when all the layers reach 2, we think that the model is perfectly optimized. And the goal of the theory is to try to get your model so that all the layers reach 2. And that's what we're trying to do, try to develop technology to do that. But, here you can, and that's sort of we see it in, just really basic experiments on things like grokking and double descent, where really, you can really flush it all out. But, you got to, we try to study small models and then apply the results to larger models. And then we go back and try to figure out what's going on. And that's what we've been doing. And it's been fairly successful. There's a lot of open questions, but, the idea of it is I give people, so that's what the spiking neurons are talking about. Is this that you can measure these signatures and you can see them in the actual models you're training, and you can use them. You can use them to make better models.
So you've mentioned grokking a couple of times. What's grokking?
Grokking is a phenomenon where if you take a model and you train it for some small data set, it m- it it tends to reproduce the training as perfect training accuracy, zero error, and people think that it's somehow memorizing the training set. And it has almost no test, and the test error is like as big as it could be. It's horrible, right? And then all of a sudden, it very quickly learns how to generalize. And so the training accuracy stays high, but then the test accuracy gets high. So my test accuracy might get like 85%, 90%. Not super high, but it gets high, very high for a small data set. That's grokking. And it's something that people it theoretically is very odd, because it's odd that you would get a model that can describe the training data perfectly. You think, well, it must be overfit. It must have memorized the data. And then all of a sudden it's able to generalize.
So the kind of non-linearity in the learning is what's interesting about.
Yeah, a phase transition, really. It just goes from not being able to generalize at all to being able to generalize extremely well. And it happens just sort of suddenly. And that's called, to grok is to understand something. So they call it grokking. Yeah.
And then generalization collapse.
Generalization collapse, something we detected. What we define is if you continue training, all of a sudden it stops generalizing. It starts going down again. So it still has memorized the training data in some sense that the training accuracy is perfect, but it starts to learn, it generalizes, and all of a sudden and it stops generalizing, and it starts going down. And it might go down to, like, instead of like on 10% accuracy would be random. It might go down to like 50% accuracy. So it doesn't get it doesn't get it does a little bit of learning, but it's confused. It's like in this state of confusion, deep confusion.
Got it. And these terms come from the title of the paper that we've referred to here, Grokking and Generalization Collapse Insights from HTSR Theory.
That's
And
my yeah. It's
HTSR theory?
heavy-tailed self-regularization. You got to have an acronym in science. Every theory needs an acronym, right? So HTSR, that's the theory. Heavy-tailed self-regularization work I published with Michael Mahoney back in 2021. So wow, it's been 5 years. Wow, it's hard to believe it's that long. So this is the theory behind WeightWatcher. This is why WeightWatcher works. Part of the theory. So what we discovered is that when people think about a model memorizing, they think, oh, the training accuracy is perfect. It must be memorizing. No, no. We actually, and it turns out that we discovered this other phase of memorizing, which is more like confusion. And so there's a state of memorization and there's a state of confusion, and they're very different. And you can detect them using WeightWatcher. Both states appear to reproduce the training accuracy perfectly.
Why would confusion reproduce the training data perfectly?
Okay, so what's happening is what's happening in these models. It turns out that in the state before grokking, we call it the pre-grokking phase. Training accuracy is perfect. Why can't it generalize? It turns out some of the layers have good quality, but some of the layers have very bad quality. So what's happened is you've learned the training data, but the layer that learned the training data, the layer that needs to learn the layer that's most important for generalizing hasn't converged.
So the idea is that it's not that you are memorizing before and then switched from like this thing called memorizing to this thing called uh generalization. It's more that part of your network is sufficiently memorized, or it's not sufficiently memorized, but sufficiently learned, right? It's converged. And other critical parts have not yet. And that's why you don't, and that's required for the generalization.
Yes. Now there's kind of someone has suggested, I saw a paper recently that said the reason it doesn't learn, there's like a numerical instability in the softmax. And so it just gets numerically unstable, and it just kind of it's trying to learn, but it just can't find its way. And you have to train it for a long period of time until it eventually jumps over the hill and learns. Confusion, or what we call overfitting in WeightWatcher, like a confusion is that now the layers learn too much information. So they're over converged. They're over baked, right? They're burned. They're cooked. They're overcooked. So they've learned too much information, and now they're stuck. And all they know is and they get confused as to what's going on because they've learned so much that now they can't generalize. So it's a different thing. So in one case, we see some of the layers converge and going down, and some of them are going to stay up here. And in the other case, they're all way down here. Like, they're all way down. They're all way too low. And what you want is you want them out here in the safe range. And that's what we're seeing. And the thing that could happen in a real model, in the real world, if you're fine tuning, you're training that you'll see some of the layers say they're down here, they're good, but some of the layers are up here. They haven't learned anything yet. They're stuck. And if you go too long, they all fall down. You burn the system. You burn it. So to me, I like the analogy of baking a cake, because it's like if you turn the oven up or you leave it in the oven too long, the whole thing will burn, right? It'll cook, it'll overcake. And so something has gone wrong. There's some numerical instability in the solver. Maybe the softmax is off. Maybe there's some goofiness in the training data. Something went wrong that's preventing the model from converging. And we can see that. And that's a different phenomenon than overfitting. And the goal is to try to, how do you fix it?
Yeah, yeah. So a couple of things jump out at me as interesting here. One is this idea of like, I don't know, really just kind of thinking about this as layers, I think, and really kind of locking in on that, I think is interesting. And then that each of these layers can be independently uh, underfit, overfit, or, in the target zone. That's interesting. But then that kind of leads me to, um, and I'm this is kind of a lead into like, to what degree have you looked at these things, or is this like, next steps here? But like, when I think about what, um, I think about like data-centric AI, or like the focus on data curation as a way to get models to perform better, more efficiently. You can also think of it in this context as like, can I construct an incremental training data set that targets the deficiencies of a particular layer or set of layers?
Yeah, yeah, I think so. I mean, that's the kind we haven't looked deeply at changing the data set as much as changing the learning rates on the layers or and making a new kind of regularizer. But I think absolutely that there's something, and because there's numerical instabilities, right. My take on data centric AI is that these guys went into industry and tried to apply their stuff, and then they realized that it's just a mess, right? Like, yeah, I've been doing this for 25 years. I tell you right now, I can't get an SVM working in production. You think you're gonna get an AI model working? You have no idea what's going on in these companies, right? So that to me is like, that's just they didn't understand like their business model, what they were selling. And it's that kind of thing where trying to figure out, how to get, how to target the data correctly. That's exactly one of the things we'd like to know, for example, is this is stuff we'd like to get into more if we could, can we figure out which parts of the data are being learned and which parts are not, right? And that you should be able to see. You pass the data through and you see which neurons light up and which ones don't. Those are the kind of things we'd like to do. Doing an ablation study on a model to figure out where in your data set is it insufficient, what part of the data do you need to fill in? Maybe like part of your data set is not fully filled in, and if you added more data there, maybe even fake data, auto-generated data, you might be able to improve training. Stuff like that. Those are things we'd like to understand better. And we're trying to, and of course, I'm trying to raise funding actually right now to do that, to develop some of this technology. Um, and I think it's just, these are things that require um just a lot of experimentation to figure out, but we definitely see it now. Like there's a paper that came out just this week from Stanford by Chris Manning about how if you look at some of these large models like Llama or Quinn, that a bunch of the layers are not learned. They're looking at how the residuals flow through the layers, and they can see that some layers are not really converging, some layers are not learning, and they're like, yeah, we told you that like 3-4 years ago. Like it's on the website. Yeah, I wish they'd used the tool and stuff, but, it's a validation of what we've been saying for some time, is that our technology can detect this without seeing the data. The other
And
reason
is there a one-to-one relationship between the characteristic that they were talking about and
I'm not sure
your
yet.
characteristic?
We're starting
Okay.
to just dig into it now. It
Okay.
is we've seen cases like we have a paper that came out where
I guess the broader point is like, this sounds like a really interesting way to characterize individual layers of models, but there are probably a ton of different ways to characterize.
well, yeah, there are a lot the main thing that we can do that no one else can do is we know the cutoffs. We know the lower bound is 2 and the upper bound is like 6. So you can use any model, you can measure the entropy, the distance, you can do whatever you want to all you can see, if you take 2 models.
Are those practical bounds or
Yeah, those are
theoretical
practical
bounds?
They they work in production. Yeah.
But
It
meaning,
really does work.
are they empirical, or are they based on some theoretical analysis, like mathematical
Combination of both.
analysis?
Combination of
Okay.
both. They're based on a combination. There's some new theory coming out. It uses techniques from theoretical physics called renormalization group. And so it's a combination of theory and experiment going together. We have theories that show there's a boundary at 2. We actually have 2 different metrics for the lower bound. And they have to line up. And when they line up, then we know. So there's some deep theory. Like I got a 100-page theoretical physics paper on this thing to really justify it, but you see it empirically as well. And this Grokking paper in particular is an important paper for us. We wrote this nice 10-page paper to really show, look, it works perfectly. And for me, the other thing is that I had somebody else do it with the tool, so it's independently verified, right? I was, I didn't, but these are real things you can use in production. I mean, they're real. Um, the challenge is, it says you have to analyze the data, and it's always tough. I mean, from a consulting perspective, look, I did a large project with Walmart. I tried to help them, fix their search engine, and you find out, oh, you need to deploy your product on our Jupyter notebook serving system. Okay. But you're a consultant. You're not allowed to have access to our Jupyter notebook serving because we put all our customer data there, including all their credit card numbers, and you can't have access to that. Okay. What do you want me to do here? I mean, that's very common. The same thing. I did a project years ago, almost 20 years ago, for France Telecom. And at the end of and we had to only use fake data. So I'm not an EU citizen. Since I'm not an EU citizen, I can't access personal data. And so what happens in these big companies is that, they'll stuff all the data on Hadoop into one system. And then it turns out they have compliance issues. GDPR, CCPA, you can't access things. So it's a huge problem. And so part of WeightWatcher is that I wanted to build a tool that I didn't need access to any data because nobody ever lets me look at it anyway. So it's a problem, and these are real production problems, and so part of, trying now to convince people, it's an easier sell to give someone a tool and analyze the model because, I mean, in a sense, I don't have the tokenizer. So I don't really I mean, I could kind of reverse engineer the model. It's kind of hard, but getting customer data and trying to look at customer data is much harder. It's a different ask. It's a different ask in the org. There are compliance issues around it. So these are things that, we'd like to try to do as a product level, but that takes some time to do.
Yeah, this is a Herculean effort to try to get around a very pragmatic organizational
It's
problem.
very hard, I always tell people, if you want to do something, you've got to. I have a friend who's figured out a way to like automate all of the marketing in his company. And he's totally obsessed with prompt engineering. He's got this, and he says, because and they won't let him do a pull. He can't do a pull request because you have to get someone to sign off on the pull request. And so he built the whole thing in Google Sheets, and Google Drive, and it's just this something an accountant would build, And but I said the last thing you want to do is be able to do a pull request because you'll get into the engineering org. And once you're in the engineering org, you have to follow their best practices. And those best practices may not work for what you're trying to do. They're best practices, they're just not best for you. And not a lot of that, we see a lot of this here is these kinds of tools, to run in an org. Part of, like I said, like why fine tuning is hard. Well, I've had people come to me, we want you to build a model for us, and we want the model and we want you to design this model for us, but you're not allowed to ever look at the data for any reason because it's a compliant. I'm not going to do. How can I possibly get it to work? I don't know how it would work, but so there's those kinds of things are real and they exist in big orgs, and so, um, looking at data and peeking, we certainly would like to look at and peek at what's going on with the tool, and this is some of the things we're trying to figure out how to do that in a compliant way.
With the in the paper, you benchmark the results against a few different approaches: activation sparsity, absolute weight entropy, absolute local circuit complexity. Like, talk a little bit about the prior work.
So in this paper, there are people at Google DeepMind and people at Anthropic, which are trying to find out metrics to figure out what's going on in Grokking. And we picked sort of the 4 top ones that people have in the theory. And what we find is that none of them can detect this third phase of anti-Grokking. None of these metrics they have, I mean, they can kind of detect Grokking, like they can see the phase transition, but because there's a threshold, they don't know what the thresholds are. They don't know that anti-Grokking or this sort of confusion phase exists, the generalization collapse. And their technique, even if they could detect it, it's not clear when it's happening and when it isn't. So that's sort of the part of the paper is not only can we detect this new phase, but none of the existing proposed metrics can detect it. Only our tool can detect it. So we just, we pick, the top ones, DeepMind and Anthropic, right? Those are the big ones, right? And so that's sort of the point is that whatever, even like they have this thing called circuit complexity, where you're trying, this is a big thing that's come out of Anthropic recently, the circuits. How do you know the circuit is overfit? Can't tell. Can't tell. Does and it may see that it has higher complexity. Or like people do compression. Another thing is, oh, if you compress, the quality of a model is correlated to how much each layer can be compressed. Okay, that's true. No question about it. Question is, what about if you overcompress? If you overcompress, you overfit. That's the third phase. They can't detect that. So that's what we're able to do with the theory is that we can detect this overfitting phase. And this is something that I'll give you an example of where it might, and it's not always bad, but let me give you an example where you might actually want to do this. We've looked at models that are like segment anything models, the SAM models from Facebook that allow you to do zero shot vision learning, right? In other words, it can, it turns out if you look at those, a lot of the early layers in the SAM models are overfit according to our theory. So here's my
Early as in base.
yes, closer to well, they're closer to the data. So you think of the early being the closer the data, the earlier the model is, closer to the label, the later the layer is. So what I think is happening is that there are these primitive features in all of vision, lines, line segments, and little circles and things like that that our visual system picks up. I think what's happening in the segment anything models is that they look at a large number of natural images and they memorize these abstract features, primitive features in the data. And that's why they're able to perform good zero shot learning. Because most natural images, in the natural environment, things are pretty much all the same. Tree is a tree is a tree. Um, and it can detect what a tree is. Because it can see, oh, that looks like a tree because it has the same primitive features. A tree in China looks like a tree in the US, although a pine tree is not the same as, whatever. Maybe a cherry blossom in Japan is not the same as a pine tree, but its primitive features are close enough that it can segment them and detect it as a tree. And that's what I think is going on. So it's not necessarily that overfitting is always bad. It might be something good. And so if you're trying to build a zero shot learning model, you might want to optimize for this kind of overfitting in the early layers. Now, I'll give you an example where it might be bad. We've looked at models like Llama Guard, these guardrail models. Guardrails show the opposite behavior. The layers near the labels seem to be overfit. And so what I think is happening, and again, this is all conjectural. I haven't gone and done ablation studies. This is all conjectural. But I think what's happening in the guard models is that it's overfitting to, whatever the examples you're giving to try to build the guardrail. And which is why they can be, you can get around them. If you can get deeper into the model and find a more abstract thing to tell the model to think about, it's able to go around the guardrail. So, maybe that if you're trying to build guardrails for models, you may need to have, and these are the instruction fine-tune components on top of Llama. So if you're trying to instruction fine-tune a model to give it a guardrail, you may want to have the overfitting go very, very deep into the back layers near the data to prevent that kind of backdooring. So we have cases where overfitting is not necessarily bad, but knowing what it is and how to detect it, um, is what we're trying to do with the tool. And so the idea is, so these are examples we've worked out, and sort of the goal is, look, we have an open source tool that's 200,000 downloads. I give it to you, try it out, and then talk to me about what you're doing. We'll see if we can figure out, what's going on, how to make it work for you. That's essentially the WeightWatcher project.
And when you compare against these other methods, are you strictly comparing against the ability to predict this thing that you made up, or are there more like objective metrics that the other labs have published
I'll
for
give you one
their?
that was very surprising.
Okay.
A couple of years ago, I took a look at all the existing base models, Llama and whatever was back. Vicuña was hot back then, this stuff. And I compared the average alpha quality metric to
Mhm.
the hallucination metric.
Okay.
And it turns out, according to our theory, the closer you are to optimality, the more the model hallucinates.
Interesting.
Yeah.
That's
So that gives that.
counterintuitive. Like what? Well, you would think that the thing that hallucinates more is not optimal in some way.
No, it's more creative, right? Right. Right. People are like, oh, we don't want them on, but other people, no, hallucination is a feature. In fact, it was so amazing. I gave a TED talk on it. I mean, it was incredible that like you think about talking to a child, like my 3-year-old niece, right? She'll just make stuff up. It sounds good. I'll make up a little story. It sounds good. I'll tell you, right? That's what they do. That's what children do. They're creative, right? They're exploring still. So these models, they seem to have this hallucination ability, seems to be related to the optimal convergence properties. And so that's an example of where we looked at that. I was like, wow, that's really cool. Um, and maybe it means that certain layers are contributing more to the hallucinations than others, right? And there's a trade-off between, thinking inside the box, thinking outside the box, right? And I always say, people want models to not hallucinate. In other words, you don't want them to be so creative. right? You don't want them going off into the tangent. Maybe you want them really to memorize the data and not be so good at generalizing. And that tells you something about what the layer should look like. And that's the kind of thing we've been able to figure out, you just using the theory and comparing to, some things other people are doing. That hopefully, I don't think people are, I don't think they're gaming maybe they're gaming the hallucination metric, but it'd be the other way. You're trying to convince people that it's not hallucinating. But we definitely, that's the kind of stuff we're seeing. And by the way, I think ours that was the only metric of all the metrics, that was the only one that actually correlated. Like the other stuff didn't really, it was just sort of random, like just random stuff. All these other, yeah, the other evals are not really correlated. Like these other evals people come up with, they don't seem to, that whatever they're doing is not as correlated with the quality metrics you have as the hallucination. I think hallucination is actually testing something fundamental about the model and how it's trained, and the other evals seem to be just maybe overfit to the data in some way. Very specific to the data you're using. So you test it on one data set, you see one thing, you get a different data set, you get something else.
Hmm. Hmm. Do you think of this as meginterp or mechanistic interpretability, or is that a tool that you're using, or
I
is
don't
that
pay
an
much.
academic thing and you're trying to
I
solve problems?
Yeah, yeah, it's an academic. I don't actually read any. There's some
Okay.
people ask me stuff like that. I don't know. What are they doing?
Yeah.
I don't look deeply at what they're doing because I know what I want to, I know theoretical physics. I know what I want to do. Um, like that's what we had. That's why it's nice to have someone come and collaborate with me, because we wrote this Grokking paper. And someone else will, I wouldn't, go out and find all these other metrics and see what they can do. The mechanistic interpretability stuff, I think my impression is that it hasn't gone anywhere, right? Like there's like, half a dozen things they've done, and what practical impact has it had on what anybody's doing? I don't know. Maybe internally in Anthropic it's useful, right? Because they're doing things specifically for their model, but a lot of it seemed very specific to specific data sets and specific models, and not something you can really apply. If I'm fine tuning a model for, Home Depot or someone like that, that's an Atlanta company, right? Home Depot. How do I use it? I don't know. So it hasn't been something that we've looked at in any depth. I'm happy to collaborate with anyone doing it. I'm happy to kind of compare what we're doing to them, but we have so many things on our plate that we just haven't looked deeply at it. So it's the same thing. Sometimes people ask me, "Well, how is your theory related to like reproducing kernel Hilbert spaces?" Some academic.
Okay.
I don't know. I've never read any of the papers. I have no. Kernel is something from physics. What do you guys? I just don't know. I mean, it's if you're doing it, you tell me. I'll explain to you what I'm doing. I'll explain to you what I'm doing, and you tell me how it's similar to what you're doing. I don't know what you're doing. The problem is there's just so much going on. Yeah, every day you wake up and, there are 1,000 new papers that have been, I think 100 ML papers being published every day. So how do you keep up with everything, right?
How
So
do you keep up with everything?
I rely on other people to come to me with interesting stuff.
Okay.
I go on, if you, that's it. I go on Twitter. I spend a lot of time on Twitter trying to see what are people talking about on
Yeah.
Twitter, and try to follow good people and listening to podcasts like this and try to keep up. But, it's everything's moving 1,000 miles, you're moving at, a couple hundred miles an hour. So you're just doing the best you can. I sort of lucked in that, I did this stuff in the 90s, and all the guys I worked with, they went off and the guys who were really sharp went off and became quants and are now running like, the investment arm of Dubai or something like this. Um, or they went off and, they went off and started companies, but most of the people in the physicists, they sort of people sort of forgot about how you could apply theoretical physics to AI. So I kinda snuck in, you know, through the old it's like an old back door in the lab that people forgot was there, and I was able to sneak in and do stuff. I think if enough people remembered all this theoretical physics stuff, that the opportunity wouldn't be there because they would have known about it, but I sort of, I got kinda lucked out that I'm old enough to remember this stuff.
You talked about the analogy in quant for all of this stuff. Like, what's the physics analogy for all of this stuff?
Well, physics and quant are very close, right? So in physics, this whole idea of we talk about self-organized criticality and the emergent signatures of emergence. Um, There's a technique in physics called renormalization group. My undergraduate advisor, Ken Wilson, won the Nobel Prize for developing a renormalization group. And it's actually a really fundamental thing in theoretical physics to understand the properties of the universe. Why do electrons have mass? Why do quarks have mass? Things like this. And how do you describe it? And it turns out that um, it can be used to describe things like when water boils. Okay, when you have water and you boil it and you see
Like
all the
phase
bubbles.
changes.
Yeah, it's a phase change. Yes. It
Yeah.
describes the phase change. It's the
Okay.
phase boundary. So renormalization group is the mathematical theory used to describe phase boundaries to describe phase changes. That's the theory you apply for WeightWatcher. And so it turns out that you can think of
It's kind of
this.
convenient that everything's a matrix.
Yes, well, I grew up in the Cold War. I learned all this math. It turned out to be useful. So it turns out like if you think about boiling water when you watch water boil and you look at the size of the bubbles. There are all sorts of bubbles. There are little bubbles, medium bubbles, big bubbles, all sorts of bubbles in the water, right? There's not like one size of bubble. That idea is those are the correlations in the system. There's little tiny correlations and there's medium-sized correlations and really big fluctuations. That's analogous to the information in the layer. So when a layer is learning, it learns little bits of correlations between the training data. It'll learn sort of medium-sized correlations, and it learns long correlations between the whole data set, across the entire data set, right? There's correlations across all the data, and they're sort of equally distributed. That's the analogy from physics. The fact that the bubbles when you boil water at the phase transition between water and a gas, that all those bubbles are basically the same or different sizes and shapes. It's the exact or they're all circular. So they're all different sizes. It's the same idea that when a layer is learning the information in the training data, it has to learn all the correlations of all the different sizes. And if it doesn't learn all the correlations, then it can't generalize that well. And if it learns and that's the idea. And if you cross the boundary, you might be you might overdo it. Or so you like you're going from water to ice, you freeze out. And if you freeze out, you get stuck. And if you freeze out, you're overfit. Right? So there's sort of this boundary between ice, water, and gas. And water is sort of it can adapt to any situation. You remember like Bruce Lee said, "Be like the water." If I pour the water in the vase, it becomes the vase. I pour it in the cup, it becomes the cup. I pour it in the glass, it becomes the glass. Be like the water. Being able to generalize is like being like water. If you don't learn enough information, it's like you've overboiled and you're a gas, and there's just no structure. There's nothing there. It's just random. And if you learn too much, you freeze, and you're like ice, and you're frozen, and now you can't generalize. That is exactly the
That's a great
analogy.
analogy.
Yeah, and because it comes from that's the physics, and it's the exact same mathematics and physical theory you use. Um, there's a I'll give you like there's a paper that came out I think today. It was if you take a reinforcement learning system and you train these models on random reinforcement, like 25% of the feedback is just random, they still get better, right? How could that
Yeah,
be? How could you fine tune a
that's
model
like
on random stuff?
RL dropout.
Yeah, it, right. It's because it's like the system is frozen and you heated it up and
Uh,
cooled it down again, and you
that's
heat it
so
up and
much
cool it
of
down.
like all these training recipes is like, how do we introduce just enough
Just
noise
enough randomness.
so that,
Yes.
yeah, yeah.
That's right out of physics. The idea of what we call spin glass theory or glass theory, that when systems become too brittle, basically they're brittle, right? They're brittle, and brittle systems are easy to bake. You think about a metal. If you want to make a metal that's not brittle, you have to heat it up, cool it down, heat it up, cool it down, heat it up, cool it down, it becomes strong. If you freeze it really quickly, it becomes brittle and it will crack. It's the same thing. And the math and the physics, all the same physics and math. Like all the math used to describe that in the physics is the same stuff I'm using to describe neural networks. It just turns out that everybody forgot it. Yeah, that's all. Because they all died. No, they're all right. They're all retired, right? I shouldn't say that. Should be they're all retired, right? All the guys have retired. They're not doing work anymore. But there's a saying in science that science progresses when old scientists pass away. Right? Because they take they stop the old guys stop the new guys from doing anything new. They don't want anything new. So when they pass away, now you can start publishing. They're no longer there interfering in what you're trying to do. But it turned out that this stuff does work. If you spend the physics theories are useful for some things, and we're trying to basically and the other thing is to me it's really important that you have an open source tool and the work be 100% reproducible. I need to be able to give the tool to somebody else and they need to be able to run it and try it. Sometimes this stuff works. Sometimes we don't get the right result. We don't know why. I don't know. What do I know? I don't. It doesn't describe. We 80% of the time we know what's going on, but 20% of the time we see things we don't understand, and we're still picking at it to try to figure it out. But hopefully the tool is still useful to people, and that's the goal of this.
So, how does the renormalization group stuff and the physics, basis of this lead to HTSR and this whole power law stuff?
So in renormalization group, there's this idea of a volume preserving a scale invariant transformation, and that's the idea. So there's a scale invariant transformation. Things operate, you have different scales. The physics, if you change the scale of the system, the physics remains the same. Just some of the numbers change. Like the mass of the electron or the mass of a quark might change depending on the scale. See this thing, the scale. Okay.
And now, is this related to like gauge invariance and that kind of stuff? Do you know that stuff?
Kind of. I do know kind of. To be technical, because I'm using a hard cutoff, technically, my system is probably not gauge invariant. So gauge invariance is a different kind of invariance. This is a scale invariance. And if you do renormalization group, like I probably need like loop corrections to do the gauge invariance. But yeah, but it turns out that so when I was formulating the theory, I was trying to understand. I have this HTSR theory. We have this alpha metric, and it seems to be this universal metric. Like every model seems to like to be at 2. Right? 2 seems to be universal. There's this random matrix theory tells you at the bottom of the universality class, there's alpha equals 2. There's a little tiny universality class in between. For some reason, 2 is special. So, I got to figure out a way to derive this from first principles. And in physics, that would be called a critical exponent, a universal critical exponent. Whenever you measure a system near a phase transition, simple systems. Um, you know, they exhibit critical exponents. They what however the change in say the heat capacity is governed by some power law, and this is a critical exponent. And it's the same thing you see in the neuroscience, the self-organized criticality, that these neurons seem to have some sort of critical exponent. They all approach the same. All the data approaches the same exponent. Maybe there's some fluctuations because it's these are small systems compared to like boiling a pot of water, with 10 to the 23rd atoms in it. So this alpha is a critical exponent. So I knew that I need to be able to figure out a way to derive this. And as I'm going through the derivation, sort of in the back of my mind, there's got to be some, critical exponents are typically associated with renormalization group. So when the renormalization group theory applies, you typically expect to see a critical exponent. So we would expect that alpha equal 2 is that. So in the course of trying to derive the HTSR theory, I realized I have to do this in order to make the math easier. I have to make this assumption about a scale invariant transformation. And then I realized, that's renormalization group transformation. Yeah. And then I tested it empirically. And it turns out that when you measure alpha equals 2, that funny power law, it turns out you can also measure the scale invariance. You can test whether the system is scale invariant by looking at the trace log of the eigenvalues. Or what's called the log determinant. So it's a log determinant relation that arises, or the trace log. So it's simple. You just compute the eigenvalues using SVD, or whatever eigensolver you want. You simply sum up. You take the logarithm of them, and you sum them up, and you start at the tail and you work backwards. And as soon as you get close to 0, boom, that's where the information concentrates. That's the scale invariance, and it turns out, and that's the connection. Now I haven't been able to prove that the alpha equals 2 is in fact the critical exponent for this transformation. I think I know how to do it, but I do stuff like that. I'm going to be living out of my car. I need to get a way to fund this operation, right? So, but I'm fairly certain that the alpha equals 2 is related to this. You can measure them both, and it turns out you can measure the scale. You can use it's called the dead X condition because the determinant of the exponent should be 1. So in the WeightWatcher, you can measure it, and you can see that if you violate the dead X condition, the scale invariant renormalization group condition, if it violates it, you seem to be overfitting. And it turns out, we didn't publish this in the Grokking paper because it was too much. because it'd be like 50, but it turns out it also works in the Grokking paper we published. So you can see the Dedex condition change. So it turns out that these two things are very related, and there's something you can actually measure. The idea, I'll tell you where the idea came from, if you're curious, is that we had this sort of side project at BlackRock. That was sort of like a side project. We were trying to figure out, can we detect when the market's going to crash? And there's this, and because the market crashed, and we're like, what if we could detect this? There's a theory by a guy named Dieter Sornay, who has this theory about why markets crash. He actually has a book called Why Stock Markets Crash. They published like 20, 25 years ago. And the theory says you can measure the signatures of renormalization group in the stock market. And I was spending our spare time. I see if we could see if we measure. And it's a different technique than what I'm using for WeightWatcher, but it starts by looking for power law signatures and looking for something called log periodic fluctuations around the power law signature. I have a blog post on it for Bitcoin. Can you detect when Bitcoin's going to crash? That kind of stuff. So it was like this hobby
Can you?
project. Well, I'm not going to trade it. I'll let you trade it. You can predict it, but can you trade it? And it was like a hobby project we were doing. Because I work with one of Dieter's classmates at BlackRock, and we were doing this. I knew about the work, and we were sort of doing this in my spare time because I knew about this renormalization. It was like one of these like crazy applications of renormalization group, and it turned out, but it was this idea that I could measure the signatures of scale and variance in a physical system. And so I had this idea. I'm like, there's a way to measure scale and variance in a physical system, and they use it to do things like, can you predict when an avalanche, like when you predict if you have a crack in a material, can you predict whether the material is going to, is a bridge going to collapse? And so you can look for cracks, basically the distribution of the cracks. And if the distribution of the cracks start following a power law, now you got a problem. The bridge is probably going to collapse. And then that's sort of like the practical aspect of it. I said, gee, I wonder if I could apply this to neural networks. And it turns out you can. It turns out it works. And we can predict when the crash, in this case being the overfitting, the generalization collapse. That's the crash. And so it turns out it works. And so that was sort of where the idea came from. Just sort of, doing sort of these, when I was at BlackRock, my job was to come up with crazy ideas to predict the stock market. Just nutty things, And the point being that only the nutty things are going to work because everyone's tried everything else. So you got to try something no one else has ever tried. Otherwise, you can't predict anything. So I would just come up with this nutty stuff all the time. This was one of the nutty ideas that we had. And and it turns out you apply it to neural networks, it actually does work. So these old theoretical physicists, they were doing, they're smart guys, right? They made the bomb. So, they know what they're doing. It does work. It's just somewhat remarkable to me that, and so that's what's going on. And I'm happy to go through all the math and be nerd out on as much as you want. But that's sort of if you derive I have this long paper. It's about 120 pages long. It's in draft form. Every week, Mike and I ask him, try to find some typos in it. Because, it's got like 500, I think it's like 400 equations.
Is it up
So
on
it's hard.
archive or something? Is it something
It's
that
not
folks
on the
can
archive
access?
yet because I don't want to put it on the archive till we find all the typos, but I have it on a GitHub repo. And it just says draft. And I'm happy to share it. If you find, like last week, we found I was missing a trace operator on one of the, in appendix A3, there was no trace. So until we get all the typos out, it's just, we don't have who has time to read this thing. It took me a year probably to write it. But it's something we'll eventually get on the archive, maybe another year. Like the HTSR theory paper, it took us 3 years to get it published. So that work was done, it was done in 2018, and we didn't get it published until 2021. It just took that long. So maybe when I retire, I'll get the CETL paper published. But, I'm happy to have anyone read it. And, it's, if you like theoretical physics and you want to nerd out and spend, a month, on vacation doing this, probably you'll get divorced if you do that. But, maybe you are divorced to give you something to do.
In the not the HTSR paper, the Grokking paper, one of the noted limitations is that you validated all this on a 3-layer MLP, and MNIST is the data set. That, in some ways, is pretty far from how you'd like to use these ideas.
Well, it's a trade-off, right? If you think about doing development of the Schrodinger equation, okay? I used to do quantum chemistry. So we run quantum chemistry on big systems, right? But you got to start with the hydrogen atom, right? You got to start, you have to start, if you're going to make a theory, you at least be able to do small things. I see it more like the Bohr atom, like what I'm doing. Mike always says that's so arrogant of you. I go, well, the Bohr atom's wrong. The Bohr model is wrong. What do you mean? You know, but it's more like the Bohr model of the atom. We're trying to come up with the Schrodinger equation. Once we come up with it, like when I was in grad school, we would study, like hydrogen dimer or nitrogen dimer, and you'd see these interesting properties. And then you have to go and apply it to big systems. So I just don't have the capital, and I'm not Anthropic. I don't have any funding for this at all. This has all been a hobby project, right? This is all my spare time. Um, I'm trying not to get divorced, if I keep working on it. But we only have so much compute resources, and we need to understand these very fundamental things. So my approach to this is we try to study small problems and understand them analytically, and do analytic theory. We have like deep. I mean, the WeightWatcher, this idea of the renormalization group. I mean, this really is 300 pages to derive the equations, and in the end, you get one metric, which is one little 10-line subroutine you can put inside the code, and you test it. And so my idea is, look, I make an open source tool, I'll give it to people. You can test it on bigger systems and see if it's useful. And that's the idea, as we we don't understand things like the Grokking, we'd like to study bigger problems. But, if you look at an attention model, there are a couple things going on. There are, like they have the attention block. And yes, well, does it apply to LLMs? Okay, well, it turns out it seems to work really, really well for the internal parts of the attention block, the K and Q matrices. It seems like even in something like Llama, where half the model seems to be overfit, not the K and Qs. The K and Qs line up really, really nicely with the theory. For some reason, the V matrix, it'll go like this, and it just blows up and comes back. Like, what happened there? So we know that, we know it works inside the attention block. Does it work for all the layers of the attention block? And if not, why not? So those are things we're trying to understand better. And it's just really hard. And those models are hard to train, right? So we're trying to look at what model, maybe BERT that people are fine tuning BERT in production, for example. That's still a common thing people do, right? For building classifiers. And so that would be like the level of model we might look at next. All of the theory has been developed on this is hydrogen model stuff, right? It's the Bohr model, right? MLP unminced. And I said, and we give the code away. Try it on fashion mints. We did some experience on CFAR 10, CFAR 100. There is a point where, it's, I would love to do it on, you know, big systems, right? But, it's compute, right? Compute's it's expensive. So being able to do observational studies, instead of having to run big experiments, instead of doing running experiments on small models, which compute is expensive, my approach is sort of like doing meta experiments by doing observational studies on hundreds of models, right? So we have a paper in Nature where we looked at like 500. At that time, there weren't that, even then, 2000, 2020, I think we did it, 2019, 2020. Look at 100 open source models. I think it was 500. We looked at 500 open source models and compared how the average metric compares to those 500 models. Today, I have a website on the WeightWatcher website. I just have, different models: Llama, Quinn, DeepSeek, Falcon. We just try to look at the big models and write up reports and show that. And that's basically the best we can. So trying to do observational studies. I'd like to study 100,000 models on Hugging Face, but that would probably bankrupt me and my VC, and I'd probably be sued. I don't know. But that's what we're trying to do.
That's awesome. Awesome. Maybe an interesting question, since you are kind of out in the field working with customers that are trying to put Gen AI to use, any beyond the stuff that we've discussed thus far, hot takes, hard fought lessons in terms of, making this stuff work?
Look, I think that the magic has been the prompt engineering, and that has opened the door for being able to do things when you don't have data, because data is so hard to get, and training models is hard. Um, and it's hard from a personnel perspective. Like, you have to pay a lot of money to hire people who know what they're doing. And if you don't know what you're doing, you can really spin your wheels and not make any progress. And the Gen AI stuff has been phenomenal. I don't think anyone really expected in context learning to work the way it does. Now, I see a lot of people trying to do, I've worked a lot in search. So I see a lot of people trying to do RAG. And then I realize RAG is old. RAG is from the 90s. That's called latent semantic analysis. That was invented in Chicago. I've been trying to do RAG for years. It never really works. And that has been, people think, "Oh, I'll just stick stuff in a vector database and it'll be fine." And, you just get all sorts of nonsense, right? I mean, it's not gonna there's no guarantee. So that I think is something people are and I've done a lot of work in search, a lot of industry work in search, and you sort of see there's a bit of a naivety about it, that there's a lot of emphasis on getting the search engine to work, the plumbing. So, right, getting the vector space, getting the documents translated into an embedding. And how fast can you do that? Because that's slow and it takes compute. And so you have to pay for that. And what size embedding should you use? And getting the vector database up and maintaining the database. And should you buy a vector database or use an off-the-shelf one? I mean, the original one was developed by Spotify, something called Annoy. There was an Annoy package a couple years ago, and then there was the one from Facebook, and then one from Microsoft, and now there are all these commercial versions. And what I've seen working with search people is that 90% of the resources or more go into these getting the thing operational. And then you get to the relevance, and you ask, "Oh, I can just do RAG and I'll get relevance." It's terrible. It just doesn't really work. And the reason is because it doesn't learn from the click stream. You wanna learn if you're doing a system where you're trying to learn from the click stream, you gotta learn from the click stream, which means you have to train a model on the click stream. And that means you either have to put some model on top of RAG.
To put that in other words, you talk to enough folks that are doing search and retrieval, like the thing that they're focused on is relevance as opposed to plumbing. And RAG, the thing that they're focused on is, that retrieval step as opposed to the generation. And what you're highlighting is this idea that, um, and also, in traditional search, like that was what they were like, that was their job. And their job was to make sure that when the user searched, they get the results that they're looking for. And it's not like a one and done. It's like, you know,
I've worked with guys from Google, eBay, Walmart, the big engines,
yeah,
right?
yeah, yeah.
And I tell you, 90% of it's just not relevance is hard. And
This is the point that I'm getting at.
yeah,
It's
relevance
hard
is
and people work on it for years.
they work over years, and people who try to get into it are very naive. And I'm not sure I've ever seen an A/B test that I believe, right? I mean, I've clients like even like I've seen clients who don't understand, like they'll put all this effort in the engineering, don't understand you have to run an AA test just to measure the variance. They don't do it. Like, okay. I mean, I've worked on internal search. Um, I've worked on internal search, semantic search. I mean, all the different variants of search. I invented technology for search. I mean, worked on eHow, first $1 billion web since Google. And it's Aardvark acquired by Google. Search relevance is widely um it's overestimated how hard it is. Excuse me, underestimated how hard
Underestimated
it
how
is.
hard it is.
And
Misappreciated for how difficult it
there's
is. Yeah.
very little good academic information. In some sense, search relevance is like trading on the stock market. The people who really know how to do it aren't going to tell you what to do because that's where the gold is. And I think that thinking that you can just do RAG and expect that to just give you good results is, are you actually you even know if you have good results? Do you even know what your bounce rates are? I mean, I've seen cases where you have search. And so part of the machine learning of WeightWatcher is like, I'd worked in search so much. I was thinking about, I want to redeploy the search engine every day. I want to retrain the model and I want to make sure it doesn't go bananas. And sort of the motivation was, how do I model the thing? I can't do A/B experiments all the time. They're expensive. A/B experiments are expensive. They're hard. They're difficult to interpret. And
You
if
need a
I'm
lot
not
of data.
in a lot of data, you have, and people do all sorts of, they'll do things in production for their A/B tests that you really shouldn't be doing. They're running multiple tests at the same time, and there's leakage between the experiments. Stuff like this. I'm like, it's useless. Like the noise is. I was trained as a physical scientist, man. I mean, I did quantum physics. I mean, I understand how to interpret experiments. You can't have error bars this big. If you're only looking at that much. And it's sort of like, what are you doing? And it's just and that part of the problem with the RAG stuff is that it doesn't take into account the click stream. And so you have to somehow do that.
Meaning, unless you've got either an implicit or explicit feedback mechanism from the user, then you're flying blind.
And you see now with AI, this is part of the problem with fine tuning. Is it really what you'd like to do is, fine tune some sort of adapter on top of the RAG to adapt it so it will work? Well, that thing has to work. Think about you're running inference. If you're in e-commerce, you've got a 200 millisecond, 250 millisecond SLA. You can't, how are you going to run inference on that? I run SVM. The SVM has it runs in 30 milliseconds. I could, it just in fact, you can run XGBoost in 30 milliseconds. You can run the SVM in under 10 milliseconds. All the overhead is based, but it's just latency from the network. But you're trying to do a model, and you're trying to do production search, and you're trying to run inference on this huge thing. You've got to boil it down. Even Facebook only uses like simple embedding models. Here's one for you. Facebook doesn't use PyTorch in production. They use Cafe 2. And they have simple, simple models. So I think a lot of what I see is what I'm seeing is that there's just, search is still very, very hard. And, RAG is not a magic box. And you're seeing now what's really interesting are people trying to do integrated LLMs that learn how to do search on the fly, right? The search is integrated into the LLM somehow. And I think it's just that's probably in terms of being in the field, like trying to get this stuff to work. And then the RAG stuff itself, you have prompt engineering issues. You have to ask the right thing. You have to get the right document. So I think a lot of that is, there's sort of a bit of a naivety about it. And so if you're trying to train, and that still is probably one of the biggest challenges I see. And again, and also because you have to track the click stream all the way through. Right? You have to track from the user, know what the user's doing. So I think there are a lot of people wanting to do this kind of stuff, and there's always a lot of money left on the table, right? To get it right. And whether this technology can help you, part of the idea is, can you fine tune a model that you can put like a little tiny model, an adapter model you can put on top of the RAG system. If you get the prefetching right, you get the broad spectrum of it, you get the document set, you can do relevance in real time with this stuff. And that's sort of, some of the motivation to doing this. And I think from the real world, you see, and of course, now we're seeing that Google, for the first time since eHow, really, is starting to lose traffic. Right, they're losing traffic, and I don't use Google for anything anymore. I mean, I use Gmail, but maybe Google Docs, but
What are you using instead?
I use OpenAI. I have O3. If I'm paying for it, I'm going to use it.
Mm-hmm.
I use it for everything. If I don't use O3, I'll use Grok. Maybe I'll go to Gemini. But Grok is O3 is problem with O3 is just slow.
It's just slow. Yeah.
But I'll go to Grok if I need something quick. Grok is quick, and then I'll go to O3 maybe for and I started using Codex. Codex is pretty cool. I'm not a cursor guy yet. I try to. I don't really like this thing. It's mucking with my code. You tell it to fix a problem, and it just erased. Codex did this morning. It erased one of my unit tests. I fixed it. It runs now. Where'd it go? It's completely gone. I like Codex because you can check the pull request. Like you make sure it doesn't delete everything. But I think that's But search to me is still like that's one of the big ones, and one of the main uses for this technology, because it really gives you a natural language interface to search. I was almost suggested the other day I wanted to remake Aardvark. Aardvark was a product that was sold to Google. I was a scientist at Aardvark, where you would ask it a question and it would go out and find someone on the internet to answer the question for you. And I wanted to integrate this into the LLM, so when it lies to you or screws something up, and you don't know how to fix it, because you're way out of you're punching way out of your weight class. You don't go find someone to fix the problem that the LLM created. Like find a real person, like find an expert to fix whatever the LLM broke. I thought that would be a good product, right? But the technology is amazing. I'm very bullish on it, but it's not a magic, you're not on the silver bullet, right? You still have to pay attention to what you're doing, but it is an amazing technology, and that's why I'm sort of all in on it, right? Sort of like, Sergey Brin said he came out of retirement just to do this. So I'm sort of like, That's what it is. It's just all day long. It's all we do now. And having worked in AI and machine learning since the '90s, it's unbelievably exciting. But it's also a little overwhelming sometimes too, which is why you have these great podcasts. You can try to figure out what's actually going on.
Yeah, absolutely. Absolutely. Well, Charles, it has been great catching up and digging into what you've been working on. Thanks so much.
Hey, thanks for the time. I really appreciate it, Sam.
All right. Thank you.
All right.